Hello everyone, and we're now switching over to corals and the thermal tolerance in corals from a very special environment, namely the Kimberley region in Western Australia. Well, Heather has already given us a very nice introduction of thermal tolerance in general, so I'm going to limit the introduction here and just want to make one point, and that is when it comes to corals, mass bleaching events because of heat stress are a major threat to coral reefs, and at least over the next few decades, arguably more so than ocean acidification. And they are becoming more frequent. The predictions, of course, vary, but we might see mass bleaching events every 5 years, already 15 years from now, and they could become annual events once global warming reaches more than 2 degrees Celsius. Sadly, as we heard yesterday already, the next global mass bleaching event may already be on the way because 2015 is a strong El Niño year, and it might be on track to become the hottest year on record. And so this graph from NOAA's Coral Reef Watch shows you the regions that are at risk of bleaching between now and the month of January next year. So the question really is, what are the upper limits of coral thermal tolerance? And will corals be able to acclimatize and or adapt to warming oceans and to keep pace with global warming? Well, naturally extreme temperature environments are ideal natural laboratories to study these questions. And the Persian Arabian Gulf or even the tide pools of America and Samoa are relatively well-studied examples of such naturally extreme environments. But only few people are aware that we actually have such an extreme environment right here in Australia, namely in the Kimberley region in northwestern Australia. In this region, water temperatures are above 30 degrees Celsius for about 5 months of the year. But what makes this region really extreme is the fact that it is characterized by the largest tropical tides in the world, with a tidal amplitude of up to 11 meters. And so there are large stretches of intertidal habitat that becomes exposed to air for several hours during low tides. And even communities that do not get exposed to air during low tide, they're often stuck in tide pools with stagnant water flow. And then the environmental conditions within that stagnant water are, of course, quite extreme. So the corals, despite these really harsh conditions in this environment, there is actually abundant coral reefs out there, and they're highly diverse. So they have adapted to these conditions, and that makes them very interesting study organisms for us. My study site is located about 2.5 hours north of Broome, on the tip of the Dampier Peninsula, and it is namely a little island called Shell Island within Sydney Bay. And at high tide, all that you can see from this island is really just the top of the island that sticks out of the water. But a bird's eye view of this area reveals that there is a lot of rocky, hard substrate surrounding this area. And so you can probably imagine that once the tides drop, and in this area it's up to 8 meters during spring tides, this area looks very different. So suddenly you get this range of intertidal/subtidal habitats that really vary in a lot of environmental conditions depending on their tidal exposure. So for example, the subtidal environment here on Shell Island only very rarely gets exposed to air, probably only a few days out of the year during the most extreme spring tides. And because of that, the corals in this environment only experience up to 3 degrees daily temperature variation. In contrast, this tidal pool in the background becomes isolated from the main water flow during low tides, and so the corals there are regularly exposed to air for several hours, often in the middle of the day. And because of that, they experience up to 7 degrees daily temperature variation, and short-term temperatures can reach up to 37 degrees. What makes these two separate environments very interesting for me is that their seasonal temperature range is, of course, very similar, and the maximum monthly mean is about 31 degrees Celsius, and also the same for these two environments. But the key question here is that very little known is about this very remote region up there, And we don't know if the corals in these environments are actually more resistant to heat stress and bleaching than corals from more traditional coral reef systems, because they are already adapted to these extreme conditions. But it's also possible that perhaps they are more vulnerable because they already live so close to a potential upper thermal threshold. And the question is also on a smaller scale whether the intertidal corals, for example, are more resistant to heat stress than the subtidal corals. Generally, there are no known records of coral bleaching in this area, and it is unknown what the bleaching threshold temperature is. So in order to find out about these questions, I conducted a heat stress experiment for which I collected 2 abundant corals from both of these 2 environments at Shell Island, the branching Acropora aspera corals and massive Dipsostrea corals. And they were maintained for the experiment in shaded outdoor flow-through seawater tanks, and they were first allowed to acclimate to natural summer temperatures for about a week, and we simulated the daily temperature fluctuations of about 4 degrees in the experiment as well to simulate the natural conditions. And so the control corals experienced maximum temperatures of 33 degrees during the day and about 29 degrees Celsius at night. And then after 1 week of acclimation, we slowly increased the temperature in the 2 heat stress treatments, which were elevated relative to the control by roughly 2 and 3 degrees Celsius. And importantly, the 2 heat stress treatments also had the same daily temperature variation. In order to monitor the stress response of these corals to heat stress, we measured the photochemical efficiency of these corals every day at noon and at night. And so at first, I'm going to show the response of the Acropora corals. On the following graphs, you will see the days of heating on the x-axis, and the experiment lasted for 11 days. And FV/FM, or the dark adapted quantum yield of photosynthesis, is on the y-axis. The ambient control corals are represented by the dark circles, whereas the 2 heat stress treatments are represented by the gray triangles and the open squares. The shaded area that you see on these graphs actually indicates a period when we had a major storm system come through, of course, in the middle of the experiment. So during that time, the temperatures, especially in the ambient control, were a little bit cooler than usually, and it also meant that there was significant cloud cover, which provided a little bit relief from heat stress. Well, one thing is already pretty clear. We observed the first significant declines in FV/FM already within a few days, and a little bit later in the intertidal corals compared to the subtidal corals. But overall, after 11 days of heat stress, the declines in FV/FM were much greater in the subtidal corals compared to the intertidal corals. And probably not surprisingly, because of these significant declines in Symbiodinium and overall coral health, we actually we saw substantial mortality in these corals because they became highly vulnerable to rapid tissue necrosis. So we observed the first mortality in less than a week, and after the 11 days of heat stress, 50% of the intertidal corals had died, and up to 75% of the subtidal corals had died, which is why we had to end the experiment at this point to have some corals left for other analysis. So clearly the intertidal corals were more resistant to heat stress than the subtidal ones, and it confirms that mortality thresholds are very close to bleaching thresholds for these branching Acropora corals. Now what about the massive Dipsostrea corals? They're generally known to be more resistant to heat stress. We generally saw similar patterns, the first significant declines in FV/FM within just a few days, but again, the intertidal corals were a little bit more resistant to heat stress than the subtidal corals. And in the end, the subtidal Dipsostrea corals didn't show as great of the declines in FV/FM at the end of the experiment compared to the subtidal Acropora corals. But nevertheless, the patterns looked relatively similar. However, the biggest difference was that we did not observe any mortality in the Dipsostrea corals. And that was despite of the fact that they were being maintained in the same tanks. So clearly, the massive Dipsostrea corals were more resistant than Acropora, which confirms known susceptibility patterns. The intertidal corals, again, were more resistant to heat stress than the subtidal corals. And mortality thresholds in this species are clearly much higher than the bleaching thresholds. For the surviving corals, we also had a look at semion densities and chlorophyll A levels, which is what I'm going to show you next. And here we have the same color scheme as on the previous graphs, but now we have the intertidal and subtidal corals grouped on the x-axis. And probably not surprisingly, we saw quite dramatic declines in semion density, up to 86% loss in the most severely heat-stressed corals. And again, the subtidal corals had greater losses than the intertidal corals. We saw very similar patterns also for chlorophyll A on a per area normalized basis, up to 91% loss for the most severely heat-stressed corals. But this was largely driven by a loss of symbiodinium cells and not so much chlorophyll A per symbiodinium, as this normalization on a per cell basis shows you. But the question now at this point is, what are the underlying mechanisms or factors driving the patterns that we saw in these corals? What is the role of the environment versus other factors? And one of the factors that could, for example, significantly influence the thermal tolerance of these corals is the genetic type of symbiodinium. All corals harbor symbiodinium clade C independent of their native environment, treatment, or species, which may come as a surprise for some of you because naturally extreme environments often harbor or have a higher prevalence of symbiodinium clade D, some members of which are known to be more thermally resistant. But these findings are actually consistent with other studies for the Kimberley region and with a high specificity for clade C in general in Western Australian corals. And even though this highlights the influence of the environment, we do have to caution that it can be quite misleading to infer the physiological performance of symbiodinium just based on the cladal resolution. So what are the implications of these findings for the Kimberley coral reefs, but also the future of coral reefs in general? Well, despite the fact that the Kimberley corals can withstand conditions at which other corals would probably die, especially when they get exposed to air, they're nevertheless highly susceptible to coral bleaching and future ocean warming. It is very difficult to put a specific temperature as the bleaching threshold for these corals because it is a very highly dynamic environment, and the fact that we had a daily temperature variation in our experiment made it more realistic on the one hand, but at the same time it makes it more challenging to find a specific temperature as the bleaching threshold. Nevertheless, it's pretty clear that even for these corals, the bleaching threshold lies just 1 to 2 degrees above the local maximum monthly mean, and that is very consistent with other places. However, the fact that the intertidal corals consistently perform better than the subtidal corals highlights that a highly fluctuating thermal environment enhances bleaching resistance more than high mean temperatures alone. And that in itself, I think, suggests that there is potential for acclimatization and/or adaptation even beyond the conditions currently experienced in naturally extreme environments. Thank you.